Good evening. Welcome back to the thermodynamic class. In the last class meeting, we have shown you how to get the properties from the table at the end of chapter 3. Now let's continue to see how do we use the table to calculate the properties of the liquid and then use it to calculate the energy balance in a closed system. So, as an example, in this case, it's shown you that a piston cylinder assembly contains 2 kilograms of water at 100 degrees C and 1 bar. So, two properties are given here, 100 degrees C and 1 bar. The water is compressed to a saturated vapor state. So saturated vapor state. So it's mean somewhere at the line on the right side of the dome, where the pressure is 2.5 bar. So saturated vapor. So this is the saturated pressure. During compression, so it's mean the pressure increases. There is a heat transfer of energy from the water to its surrounding having a magnitude of 250 kilojoule. Okay. Neglecting change in kinetic energy and potential energy, determine the work in kilojoule for the process of the water. Okay, so the process is a compression, and then there is a heat transfer from the system to its surrounding. And the question is, what is the work, W? Okay, so if you see on the bottom left figure here, it's showing a schematic of the system. So we have 2 kilograms of water, and there is a black dashed line there. This represents the boundary of the system. And then the system is contained within a piston cylinder assemble. So here you see a piston with a gray color here. And then state 1, it is at 100 degrees C and then 1 bar. And then the system is doing a compression process. So the pressure increases if it's doing a compression process. I think the volume also decreases. So the piston moves to the left. And then the state 2 is at saturated vapor, and the pressure is 2.5 bar, and there is also a heat transfer from the system to the surrounding. So it's mean here Q is from the system to the surrounding. Therefore, following the convention, it has a negative sign here. Q equal to minus 250 kilojoule. Okay, if you look at on the right side, so we have a TV diagram. So the system start at point 1, state number 1, and now you can open, let's say, go to table A2, so where you can see the properties of saturated state based on the temperature. Go to table A2 at 100 degrees C and check what is the corresponding saturated pressure there. And you will see that the pressure at state 1, P1, is slightly lower than 1 bar. So, because the pressure at the corresponding temperature is lower than the saturated pressure at the same temperature, so the state is, it's called a superheated condition. You can do the same thing using table A3. So look at the table A3, pressure equal to 1 bar, and then see what is the temperature, saturated temperature at a 1 bar. and you will find out that the saturated temperature at 1 bar is slightly below 100 degrees C. So it's meaning here state number 1 is at the right dome, at the right side of the dome, slightly, because you can see that the temperature difference between the saturated temperature and 100 degrees C here is very small. So you can put the point number 1 slightly on the right side of the dome, and it is at the pressure line equal to 1 bar. And then the system is doing a compression work to state 2, and this state 2, it is saturated vapor at 2.5 bar. So you can see in here I have the second pressure line, and this is at 2.5 bar, and point 2 is at the saturated vapor line here. Okay, so in here you can draw a line connecting state 1 to state 2. So other known condition here, or other known parameter here, is that the Q is 250, so going from the system to the surrounding. Okay, so now go next. You can apply an energy balance for the closed system using this formula. So delta KE plus delta PE plus delta U equal to Q minus W. And we know that the first two terms on the left side here equal to 0. So the chain of the kinetic energy and the chain of the potential energy are neglected here, so you only have delta U equal to Q minus W. Q is given there, minus 250 kilojoule. Work here is what is asked by this problem, and delta U can be obtained from the table. So in here you have a simplified formula here. The W equal to Q minus M time U2 minus U1, U small. So in here, this one is specific internal energy. So this is the internal energy per 1 kilogram. And capital U here is the internal energy. So the unit is kilojoule. So what is not known here on this equation is U2 and U1. So now you can use table A4 to get U1. So if you remember, table A4 here is show the water properties under superheated condition. So you go to table A4 and then find out what is U1 at 1 bar and also temperature at 100 degrees C. So you can see here that from table A4, check it by yourself, that you will see U1 equal to 25 euro 6.7 kilojoule per kilogram, and the data is there. So 1 bar 100 degrees C is available in the table, so you don't need to do any interpolation there. So it's ready to go. And then the next one is to get data for U2. So state 2 is saturated vapor at 2.5 bar. So saturated properties based on the pressure, then you need to use table A3. So now go to table A3, saturated vapor. So U2 equal to UG, and 2.5 bar you can see the data of UG at 2.5 bar, and it is 2537.2. So you have U1, you have U2, M is given, and then Q is also given. Then you can get the work here. So you just plug in all number here, and you will have this work. So it is minus 311 kilojoule. It's minus, it means the work is done on the system. This makes sense. Why? Because the process from state 1 to state 2 is a compression process. So to have a compression process, a work must be done to the system from the surrounding. Okay. Go next. Another example, water contains in a piston cylinder assembly. So once again, the system condition or steam shape is the same. A piston cylinder assembly undergoes two processes in a series from an initial state where pressure is 10 bar and temperature is 400 degrees C. Okay, so state 1 is given here. So as initial state here, state 1, so 10 bar, 400 degrees C. Okay, and then two processes in series. Process from state 1 to state 2, the water is cooled as it is compressed at constant pressure to the saturated vapor. See here, so there are two messages here. The water is cooled, so it means there is a heat transfer from the system water to the surrounding. And then the second message is it is compressed, so it means there is a work there. The work is done to the system. Okay, and this work is applied to the system at a constant pressure. Okay, delta P equal to 0. And then the second process, the water is cooled at constant volume to 150 degrees C. Okay, process 2 to 3, the water is cooled at constant volume to 150 degrees C. Okay, the first question is sketch both processes on TV and PV diagram. And then second question is for the overall process, determine the work. So it's mean what is the work for the process 1 and what is the work for the process 2. And then the third question is for the overall process, determine the heat transfer. So Q total here. Okay, let's try to solve this. Okay, let's solve this problem. As I show you in chapter 1, so you need to follow the step there. So first is what is known for this problem. For sure it is a water contained in a piston cylinder assembly undergoes two processes. Okay, process number 1, there's a cooling and compression there while the pressure is kept constant. And the second process, the system is cooled at constant volume, so delta V equal to 0. Second step is what do we need to find? First is we need to sketch the processes on both TV and PV diagram, and then we need to determine what is the net work and the net heat transfer from these two processes. So next step is we need to make a schematic. So this is a water system contained in the piston cylinder assembly. So you see here I have water, and then you see a dashed line here. This is a boundary separating the system from the surrounding. And then the next step is you need to write it down what is the engineering model or the assumption. So first assumption here is that the water is a closed system, so there is no any leakage there, so the mass is constant. And then assumption number 2 is that the piston is the only work mode. So in real application there might be other work mode ongoing, And number 3, so delta KE and delta PE equal to 0. And then let's go to the first question, sketch on both a TV and PV diagram. On the bottom left figure, here is the PV diagram. So first, what we know here is that state number 1 go to state number 2 and doing a compression process. So in state number 2, state number 2, it is saturated condition at pressure equal to 10 bar. So if I go back to this PV diagram, there's a compression process. Okay, compression process from state number 1 to state number 2, and state number 2 is at the saturated vapor line. So for sure, state number 1 must be on the right side of state number 2. Why? Because it is compression process. So pressure from state number 1, volume from state number 1 will decreases and go to volume at state number 2. So in here, I know that state number 1 is superheated condition. If you're not sure, like what we saw in the previous problem, check it on either table A2 or table A3. So if you use table A2, then go to the given temperature at state 1 and then check it what is the saturated pressure at that temperature. So go to table A2 and temperature 400 degrees C and check what is the saturated pressure, and for sure it will be lower than 10 bar. Okay. Similarly, you can also use table A3. So saturated properties based on the pressure. So go to table A3 and then look at 10 bar what is the saturated temperature, and you will see there that the saturated temperature at 10 bar is lower than 400 degrees C. Therefore, state number 1 is superheated condition. So from state number 1, let's go to state number 2 at constant pressure. So that you can see in here that the line connecting state 1 to state 2 is a horizontal line because the vertical axis here is a pressure. And then from state number 2 to state number 3, the process is conducted at constant volume. So see here, it's straight vertical line. So V2 equal to V3. Okay. Similarly, if you go to the TV diagram on the right side, so state number 1 is superheat condition here, and then it's following a constant pressure line. So this is a constant pressure line. So let me redraw here. This is a constant pressure line at 10 bar. So from state number 1, let's go to state number 2 at saturated vapor, and then from state number 2, let's go to state number 3 at constant volume. So you can see in here, state number 1 is superheated, state number 2 is saturated vapor, and state number 3 is a mixture between liquid and vapor. Okay. Go next. So now we are ready to do the analysis. Okay. And then A, we have answered it, the sketch on both PV and TV diagram. So once again, state 1 is given here 400 degrees C, and then P1 is given here 10 bar. Okay, so in here also shown that at 10 bar you have the corresponding temperature of 79.9 9 degrees C, so it's way lower than the given temperature here, 400 degrees C. Therefore, state number 1 is a superheated condition, so it is located on the right side of the dome. So B is a question regarding the net of the work. So in here we apply the same formula when we calculate the work in chapter 2. So W equal to the integral P dV. So in here we have two processes here. So the first term here represent the work from state number 1 to state number 2, and then plus the work from state number 2 to state number 3. So P dV. And if you can see in here, the work from state number 2 to state number 3 is 0. Why? Because dV equal to 0. Okay, there is no change of the volume from the process from state number 2 to state number 3. So the only work happens from these two processes in series is during the process number 1. So in here I have this formula. So it is integral P dV from state number 1 to state number 2, and it occurs at constant pressure, so pressure can go outside the integration, and then we only have work equal to P times integral dV. So integral dV is for sure the volume change between these two boundary. So here is between these two states. So it's state volume at state 2 minus volume at state 1. And then I have the pressure, so 10 bar. And then now what we need to find out is the specific volume at state 2 and state 1. So for the specific volume at state 1, which is at superheated condition, then you need to use table A4. So now go to table A4 at find out the specific volume at 10 bar and temperature 400 degrees C, and you will get this number. And then for state 2, V2, it is a Vg, and the given properties here is a pressure. So you need to use table A3. Okay, use table A3 and then look at the Vg at P equal to 10 bar, and you will get this number. So you have all number 10 bar, and then the equation I believe is in kilojoule per kilogram. So therefore you might need to convert this bar into the Pascal first, and then you will get the unit in joule, and then you divide by 1000 to get the result in kilojoule per kilogram. So you can see in here 10 to the power of 5 here is the conversion from bar to Pascal, and then you will have the work in joule per kilogram, and then you divided it by 10 to the power of 3 to convert the unit from joule per kilogram into kilojoule per kilogram. So we have a minus here, minus, so it's mean the system is receiving a work from the surrounding. Okay, go to now to C. It is the question for the net of the heat. So here we apply first law of thermodynamic. So on the left side we only have the internal energy change, because delta KE and delta PE equal to 0. So delta KE equal to delta PE equal to 0. Therefore you only have the change of the internal energy only. So delta U equal to Q minus W. So Q equal to delta U plus W, and then you divide each term by the mass, by M. So you have here Q divided by M equal to U3 minus U2 plus W divided by M. So for U1, you can still use table A4. Okay, you can use table A4 to get U1. And if you look at the PV or TV diagram, state number 3, it is inside the dome. So it means it is under two phases there. So in here, state 3, we know that it is obtained from state 2 when the system undergoes the process at constant volume. So it's mean V3 equal to V2. Okay, V3 equal to V2. And then another properties that we know from state at point 3 is T3. Okay, so to fix the state at point 3 in here, we need to know what is the quality. What is the quality of the mixture at state 3. So in here, you can see here we have this formula for the quality. So it is V3 minus VF3. So this is the specific volume at saturated liquid based on T3 divided by Vg3. So this is the specific volume at saturated vapor at the given temperature here, T3. Okay, so in here you use table A2 because it is saturated properties based on the given temperature. So go to table A2 and then at temperature 150 check what is the Vf and what is the Vg, and you will have this number. And then if you plug in all value there, you will have the quality at state number 3 here is 0.494. Okay, so once you have X3, now you can calculate other thermodynamic properties. What we need here is U3. So in here I can calculate U3 using this formula. So you can see on the previous slide I showed you last week how to calculate UH for the next one, S entropy for the state within the dome with a given X. So this is the formula. So you plug in all number there. Once again, you use a table A2 to get UF and UG, and you plug in all number there, you will get U3 equal to 1584 kilojoule per kilogram. So once you have U3, you go back again to this formula and you plug in all number, then you will have Q over M equal to minus 1485.5 kilojoule per kilogram. So it's mean here that there is a heat transfer from the system to the surrounding. This is the minus sign there. The next properties is specific heats. So in here we have 3 properties here related to the specific internal energy and also specific enthalpy. So small u and small h. So in here we have Cv. So Cv is defined as the change of the internal energy to the change of the temperature at constant specific volume. Similarly, Cp, so this is specific heat at constant pressure. So this is delta H over delta T, equation 3.9. And then the third properties here is the ratio of Cp over Cv, so equation 3.10. So once again, K here is specific heat ratio. So in general, Cv here, it is a function of phi and T, or P and T. And then Cp here, it is a function of both P and T, or phi and T, okay? And then you can get this specific heat data from figure 3.9, or you can also get it from table A19 through A21. Okay, now open your table again, go to table A19 through A21. Try to be familiar with this table when you are asked about the specific heat of certain matters there. Okay, so in real application, usually people talk about Cv and Cp here as a specific heat that relate the value of showing how much is the heat that need to be applied to the matter to increase the temperature by 1 degree. So once again, usually people represent a C with a Cp or Cv here to represent like how much is the Q, so that delta T equal to 1. So if material has a higher Cp, so it means it required higher heat to increase the temperature by 1 degree. Okay. And this Cp material is very important when we deal with research about the coating properties of metal applied to a piston, applied to exhaust system, and so on. Okay, so this is a figure showing the Cp and okay, both Cp here, but at different units. So on the left side here is showing Cp in SI unit, and then on the right side is Cp in British unit. So you see here that the horizontal axis is temperature, and then vertical axis is Cp for sure, and then it shows the Cp as a function of temperature and pressure. So the orange line here is a constant pressure line. So you see here, this is 50 megapascal, and then going to this direction, the pressure increases 41, 31, 25, and so on. Similarly, on the right side, you also have Cp as a function of temperature and pressure here in SI unit. So once again, try to be familiar with this figure or table A19 up to A23 to get the Cp of different material there. So next topic is about incompressible substance. So I believe you are familiar with incompressible thing. So you learn it in physics or maybe basics chemistry as well. So for a substance that is modeled as an incompressible, so it's mean we have first assumption here is that the volume or specific volume is constant, so delta phi equal to 0, and then the next one is that the specific internal energy is only a function of temperature. So in here, for a substance that is modeled as an incompressible substance, it has a Cp equal to Cv. So if Cp equal to Cv, what is the value of K here? So if you remember, K equal to Cp divided by Cv. So for incompressible substance, specific heat ratio equals to 1. So once again, for substance model is compressible, we have only one constant of the specific heat, so usually it's represented by C, and then we can use equations 3.20a and 3.20b to calculate the change of the internal energy, delta U, and the change of the specific enthalpy. So the change of the internal energy equal to C times delta T, and then the change of the enthalpy, which is the change of the U, so C times delta T, and plus V times delta P here, so P2 minus P1. So in equation 3.20 here, usually the contribution of the second term, so equation 3.20b, so the contribution of V times delta P usually is very small, and most of the time it is neglected. So you can see in here, if you neglect the second term of this equal to 0, you see there that delta U equal to delta H. So this is for an incompressible substance. So next topic is about universal gas constant, and I believe you also familiar with this. It's capital R. So in here it has the bar line here. So if you remember, all parameter with the over bar line here is molar basis. So it's mean this is per mole, not per kilogram. So now let's have a look on the chart here. So imagine we have a gas and it's confined in a cylinder by a piston, and then the entire assembly here held at constant temperature. So if you change the position of the piston once again while it is held at constant temperature, then you will have a process line following this line. And for example in here, if I reduce the pressure, and then it's going to the left, and all the way it will be at this point. And then I can also change the temperature of the system. Let's say now I have T2, and same thing, I decrease the pressure while I hold the temperature constant, and the process will go to the left, and finally it will be at this point. And then I change to T3, T4, and maybe in here I also have a T5. Similarly, it will go to this general point. So in here I have a general point which is called universal gas constant. So it's called universal. It means this number is the same for any material, for any substance. So I also have the formula in here. This is based on the phenomenon we have on the testing. So limit P times V divided by T when the pressure going to 0 approach 0 point here, it's equal to R here on scale, and R here is called universal gas constant. So we have different number of R here depending on the unit that we use. So most of the time we use SI unit here. We have 8.314 kilojoule. Okay, some people use 8314, but this is in joule. Okay, 8314 joule per kilomole Kelvin, or we have 1.986 BTU per pound mole degree Rankine, or we also have here 1545 feet pound force per pound mole degree Rankine. So go next, compressibility factor, or it is represented by a Z here, capital Z. The compressibility factor here is dimensionless ratio. So it is defined as the ratio of P times phi. So here phi once again with the over bar. So phi here will be cubic meter per kilomole. Okay. So because this is once again molar basis. So Z is defined as the ratio of P times phi divided by R times T. Okay. And then with this formula that phi over bar here equal to M capital, so this is molecular weight, times phi specific volume, so the unit is cubic meter per kilogram. Then you also have the formula for Z like this. So it's there. This is P times phi divided by RT. This is because R here equal to R over bar divided by molecular weight. And then in the previous slide, because limit of P times phi divided by T for the pressure approach 0 here equal to R. So I can also write it down here, and that for pressure approach 0, limit of Z here equal to 1. So if you look at on the right feature here, on the horizontal axis I have a pressure in atmosphere, and then the vertical axis here I have Z, and then this red line is the constant temperature line, so it's different temperature. So you see there, if I decrease the pressure and it goes approaching 0 here, I have Z equal to 1, which is what we have here on this one. Okay, so once again, for pressure approaches 0, I have limit of Z equal to 1. So this table is showing a gas constant R. So remember, this is R without over bar. So it's mean here it comes from R over bar divided by molecular weight. This one is that it's universal. Okay, this one is universal. But R is not universal because it's depend on the molecular weight here, molecular weight of the individual substance. For example, I have water here, H2O. Molecular weight of this water is, I believe, is about 2 plus 16, right? So hydrogen has molecular weight of 1, but I have H2 here, it's 2, and then oxygen has molecular weight of around 16. So in here, molecular weight of water is around 18. I say around because actually it might have like 18.0 something there. Okay, so now if I divided this R over bar by molecular weight of the individual substance, I get here R for each substance as well. Okay, so this is very popular for air. So it is 287 joule per kilogram Kelvin, or 0.287 kilojoule per kilogram Kelvin. And I also have this one for water. Now let's have a look again to this compressibility chart. If we modify this parameter, for example, for the pressure, I have PR here. It's called reduced pressure, and this PR is defined as the ratio of the pressure to the PC. So remember, PC critical pressure. Similarly, if I modify the temperature from T to be Tr, so this one is defined as the ratio of T over Tc, critical temperature, then I have this generalized compressibility charge for different substance in here. So for different substance, I have a general charge here. So for example, this one is for Tr equal to 2, and then going down here, Tr decreases 1.5, 1.3, and so on. So as you can see in here, if I have higher Tr, Z is about 1. So it means the substance has a very high temperature. Or, once again, if I have a lower pressure, so it means here P over Pc decreases, it doesn't matter what is the value of Tr, then Z equal to 1. So once again, Z is defined as PV over RT here. So, in the chart of this generalized compressible, the compressibility factor Z, so here once again we plot it against PR and TR. So I have formula here, so I have Z equal to PV equal to RT, write it down here, PR and TR. So now I have also write it down again here, the formula for capital or for R with upper bar. So this is equation 3.22. So the same thing like on the previous slide. But in here, what is different from the previous one is that I have PC and TC. And I believe I show you on the previous class meeting that we can get this PC and TC from table A1 or table A1E for the British unit. So when the list of this parameter is used in consistent unit, and then Z, PR, PR here is numerical value without the unit, so it means it is unitless. So in here, let's take a look on this example. I have air, temperature is 200 Kelvin, and pressure is 132 bar. So I have, so now go to table A1 and get TC and PC at this condition. Oh, sorry, PC and TC for air. So PC and TC is independent of the condition. So it's just a function of the substance there. So from table A1, you can see that TC equal to 133 Kelvin, and then PC equal to 37.7 bar. With these two numbers, you can get TR equal to 1.5 and PR equal to 3.5. So with these two numbers, now you can use the chart here to get the value of Z. Okay, so I have PC equal to 3.5, so it's somewhere here, and then TR 1.5. 1.5, it should be, oh, here I have this one, and then you can go to the left that you will have Z equal to 0.8. Okay, so with this compressibility chart for a given pressure and temperature, you can get Z. Okay, good. So another alternative form here, as shown in the previous slide, that you have this one, Z equal to PV divided by RT, no upper bar here, so everything is in kilogram basis, And then I also show you already previously that R equal to R over bar divided by M. Okay, so now let's go next. So in here we study the generalized compressibility chart. So in here I have the solid line. Once again it's labeled as a TR. So if I going down I have different TR values, so it decreases. And then the message for this chart is, you see there that this line is built based on the scattered point. So this scattered point is from the test data. So due to some inaccuracy of the equipment and then standard error and so on, you might not get a perfect point forming the line. But however, you can also build this line around this scattered point using a curve fitting, so that you can see here the general trend of this scattered point. So if the pressure in here is reduced pressure is going or approach 0, then you have compressibility factor close to 1. So let's have a look on this chart that at TR equal to 1, so here the lowest TR line here, I'm going here. In here you can see that Z vary from 0.2 and then up to 1 here. So this is the variation of Z for TR equal to 1. And then you will have less variation of this Z as TR takes higher value. Example, if you go up, for example, go to the extreme one here is TR equal to 2. See in here the variation of Z is just this one. So very small variation. So it's close to 1. As I mentioned to you in the previous slide, that if I have a substance with high temperature, so the compressibility factor Z is around 1. It's close to 1. Okay, go next. For each specified value of TR, compressibility factor approaches a value of 1.0 as PR approach 0. I mentioned it several times. So here once again, doesn't matter whatever the value of TR, if PR, which is a P over PC, approaches 0, then Z, compressibility factor here, approaches a value of 1.5. So in here I have a simple animation. I have blue dots here, and then you can see here if I play around this one, I will have this blue dot going to the left. Let me see how can I play around with this. Looks like I cannot play around this one. Let me check. Oh, it's working now. Okay, see there the blue dots there is going to the single point Z equal to or around 1.0 when PR close to 0. So lower value of PR where Z equal to 1 do not necessarily correspond to a range of low absolute pressure. Once again, this is important. So low value of PR do not necessarily correspond to a range of low absolute pressure. This will show you the number there. So see, if I have PR equal to 0.05, then I have P equal to 0.05 times PC. Remember that PR equal to P over PC, right? So now go to table A1 and then see one by one water vapor. There you see that PC equal to 220.9 bar. If I have PR equal to 0.05, then I have the pressure of the water vapor is 11 bar. 11 bar is not a low pressure, it's high pressure. Okay, low pressure maybe is close to 1 atmosphere, 1.5, 1.2. but 11 bar is very high. Although it's not that high compared to, for example, the pressure during the combustion process within the engine, but 11 bar is high enough. Then go to the ammonia. Ammonia from table A1, it has PC 112.5.8 bar. So here I have 5.6 bar operating pressure there with PR equal to 0.05. So PR looks low there, 0.05, but P still some number there, 5.6 bar. Carbon dioxide, for this 0.05 PR, I have 3.7 bar operating pressure. Air, 1.9 bar. So this value within the box, so 11 bar, 5.6, this is in engineering practice are not normally considered as a low pressure. So it's some number there. It's not a low pressure. Let's take a look on this example. So this example will show you how to the utilization of the generalized compressibility chart. So in here I have a closed rigid tank filled with water vapor initially at 20 megapascal. So 20 megapascal is mean 200 bar. Temperature 520 degrees C. So it is cooled until its temperature reaches 400 degrees C. So it is cooled from 520 to 400 degrees C. And then using the compressibility chart determines, first question here is the specific volume of the water vapor in cubic meter per kilogram at the initial state. So at this initial state, 20 megapascal and 520 degrees C. And then the second question is the pressure at the final state in megapascal. So closed rigid tank, so it's mean no transfer of mass within the system. Rigid, so it's mean there is no change of the volume. Okay. So as usual, you need to do several steps here. What is known there, water vapor is cooled at constant volume from 20 megapascal, and then from the megapascal, and then temperature of 520 to 400 C. The question is using the compressibility chart. We need to calculate the specific volume and the specific volume at state 1 and the final pressure. Okay, so next step is the solution. So first I have schematic here. So water vapor, it is cooled. So in here, to represent the cooling of this water vapor, we put ice block at the bottom of the system. So there will be a heat transfer from the system to the surrounding. Initial condition is given here. Final temperature is also given. This is the assumption. Water vapor is a closed system and rigid, no change of the volume as well. The initial and final state are at equilibrium, and also here, this is the volume is constant. This is coming from the information that it is a rigid system. So look at on this compressibility chart. I can start looking at state number 1. So in here it is water vapor at this temperature and this pressure. So from table A1 I can get what is TC and PC, right? From the PC and PC in table A1, I will be able to get what is PR and TR, so that I can locate the location of state number 1. And then state number 2, what is known here is the temperature. So and the volume stay the same there. So the specific volume stay the same. So in here I have R1, I have PR1, and then from the compressibility factor formula I have that Z equal to PV divided by RT. So in here I have V1 equal to Z1 times R times P1. And then Z1, you can get it from the compressibility chart, the previous slide. You will get around 0.83. If you get different number, I can understand it, because use a table depending on the accuracy, and also once again, each people might have a different number there, and I can understand it. Some people get 0.83, the other 0.82, the other 0.85. It's no problem there. But if you have completely different number, yeah, then it means that you have an issue to read the table there. Okay, so I have this formula. I have R over bar, universal gas constant. I have T1, I have P1. Then if I plug in all this number, I will get V1. So I get V1, and then in here, this is the V1, so the specific volume at the initial state. So we already answered it for the question A, so the specific volume at the initial state. The second question is, what is the pressure at a final state? So in here, we introduce one new parameter here. It's called R with single prime here. So it is defined as V times PC divided by R divided by DC. So in here, if I plug in all number, so once again, process from state 1 to state 2, it is a closed system. So, and then it's rigid, so it means there is no change of the volume. Okay, so it's rigid, so it means V2 equal to V1. So in here, I can plug in this V from V1 times PC, you get from table A1, divided by R, and then divided by DC. Then I will get VR single prime 1.12. And then state 2, the temperature is given 673. And then from table A1, we get TC. Then I have TR2 here equal to 1.04. And then go back again to this generalized compressibility chart. I have state number 1 here, and then let's go to step number 2 following constant V. So in here VR equal to 1.15. So this dashed line is the line for different VR. So in here VR 1.12. So and then go to state number 2 here. Beside the given V of the calculated VR single prime 1.12, in here we also have TR2 1.04. So in here you have two number here that you need to map it to this chart. You might have 0.2 somewhere here, and then you draw a vertical line, and going down it will cross the horizontal axis at some portion here. So you might have PR2 is around, let's say, 0.69. Once again, you might have 0.68, you might have 0.67 or 0.71. It is reasonable. And then so once you have PR2, you can calculate P2 equal to PC times PR2. So PC, once again, you can get it from table A1. So you have 22.09 times 0.69. So you will get a value of 15.24 megapascal for the pressure at state 2. Next example. So in here, we are asked to determine the volume occupied by 2 kilograms of water at 100 bar and 400 degrees C. First, we need to use a compressibility chart, and second one, we need to use a steam table. Okay, steam table. So, okay, we have this system, and then once again, you need to follow the step there, what is known there, what you need to find out, and then solution, and then you make to use or you need to define to formulate the engineering model or assumption, and then next step you need to go to the solution. So the first question is we need to use a compressibility chart. So here from table A1 again, you will get what is PC and TC for H2O, and then using this formula you will get PR and TR. So you have PR equal 0.45 and then TR equal to 1.05, and then now go to feature A1. Okay, go to your feature A1 and estimate what is Z there. So this example showing Z equal to 0.86. Once again, you might have a different number close to 0.86. Okay, so try to be familiar on using this feature A1. So how do we get Z? Based on a calculated PR and TR. So once you have a Z, now you can calculate the volume, specific volume, using this formula. So specific volume equal to Z times R with upper bar, or a time R with upper bar divided by molecular weight, which is actually this one is R. So phi equal to Z times R times T divided by P. So you plug in all number. Don't forget to apply the conversion factor here. So you need to convert it from bar to Pascal or to Newton per square meter. So divided by 10 to the power of 5. And then you need to convert it from joule to, you need to convert it from kilojoule to joule, because in here I use R in kilojoule, 8.314. Okay, so when you plug in all number, you have the specific volume of this one. So you have the specific volume, mass is given here 2 kilogram, then you should be able to get what is the volume. So multiplying m times specific volume, you will get 0.0534 cubic meter. So you have this number from the compressibility chart. Now we need to compare it with the one from the table. So 100 bar, 400 degrees C. If you are not sure which condition is it, as we shown you in the previous slide, you can use table A2 or table A3. If you want to use table A2, go to temperature of 400 degrees C. What is the pressure? If the pressure is below 100 bar, so it means it is superheated. If the pressure is higher than 100 bar, it means it is subcooled or compressed liquid. So in here, it is superheated condition. Go to table A4, 100 bar, 400 degrees C, you will get the specific volume, 0.02641. See here, you have this number compared to this number. It's not too far, okay? Then you can get also volume here. Multiply m times a volume, you will have 0.053. Here you have 0.0534. It's close enough, okay? So in here it's also calculated different. It's 1.1%. Yeah, it's reasonable because you will have a higher, or you will have a less accuracy when you use a chart compared than use a table. Another example shown in this figure below, we have a refrigerant 134A is contained in a piston cylinder assembly. Initially it is saturated vapor, okay, saturated vapor. The refrigerant is slowly heated, so Q is applied to the system here. So Q is going into the system there. It's slowly heated until its temperature is 160 degrees C. Okay. During the process, the piston moves smoothly in the cylinder. So it's when it's said move smoothly, there is no friction there. For the refrigerant, evaluate the work in kilojoule per kilogram. Okay, so the pressure at the atmosphere is 1 atmosphere. There is a weight of the piston here. Okay, the weight of the piston. So based on this information, you will have the pressure of the refrigerant there, right? And then initial condition, saturated vapor. Okay, saturated vapor, the pressure is from this. Then you need to use table A3, right? Okay, and then final condition is T2 at 160 degrees C. It is heated, so from saturated vapor. So it's mean the state 2 here will be superheated. It will be on the right side of the dome. Okay, so here you need to write it down what is known, what you need to find out, schematic, and then you can plot the process in PV or TV diagram, doesn't matter. You have state 1, saturated vapor, and you should be able to get the pressure based on skin. Atmosphere pressure is given here, and then the weight of piston is given here. The cross-sectional area is also given there. It is heated, and then at constant pressure, so you have a process line which is a horizontal line from state 1 to state 2, so it's here. Okay, and you also need to formulate the engineering model. So it's closed system, and then during the process, refrigerant is slowly heated and piston moves smoothly, so no friction. And then you also make assumption number 3, volume change is the only work there. So once again, the PdV is the only work there. So now, first you need to calculate what is the pressure, right? So if you remember in chapter 2, we can apply a free body diagram here to get what is the pressure here. So once again, there is a pressure from the surrounding, and there is a weight of the piston. If you apply a free body here, balance of force, you will get the pressure here, which is 16 bar. Saturated vapor with a given pressure, so then you need to go to table A3, right? You need to go to table A3 to get what is V1 there. What is V1 there? Okay. So once you have V1, and then you know the pressure, and so it's constant pressure. It's constant pressure, and then state 2 has the same pressure as state 1, and then temperature is given. Then you use table A4 to get what is V2. Okay, V1 you get it from table A3 at the 16 bar. Then you plug in all number, then you should be able to get the work there. So P times dV there. Okay, good. Next example, I have a piston cylinder assemble again, containing water, initially liquid at 50 degree Fahrenheit, so undergoes a process at constant pressure. Okay, so P1 equal to P2 at 20 psi. Okay, to a final state where the water is a vapor, so vapor at 300 degree Fahrenheit. So in here, delta KE and delta PE are negligible. The question is, what is the work and Q in BTU per pound for each of the 3 parts of the overall process? So from initial liquid state to saturated liquid, and then from saturated liquid to saturated vapor, and from saturated vapor to the final state, all at 20 psi, because it's constant pressure process. So you need to write it down, what is known there, what we need to find out. So we need to find out Q, we need to find out W for each of the 3 parts of the process. And then you need to make a schematic here. So you have 3 process here, 1 to A, here to you have B to C and C to D, and this is the engineering model. Okay, so assumption, so the water is within the piston assembly, a closed system, and then constant pressure, no change of the kinetic energy and potential energy. Okay, and then see here I have the process sequence, the process here. So one here going to A, and then going to B, and then going to 2. So one is subcooled or compressed liquid, and then A is saturated liquid, B is saturated vapor, and then 2 is superheated condition there. And here I have the formula of the work, integral P dV, and this is the energy balance from the first law of thermodynamic, equation 2. So what you need to do it there is you use different table to get the thermodynamic properties. Use table A2 for the saturated state with a given temperature, and then use table A3, the same thing but for a given pressure, and A4 to get the data at state number 2. Okay, in here at state number 1 we use this approach so that V1 equal to Vf at the same temperature, and also U1 equal to Uf at the corresponding temperature, which is T1. So you can make a simple table here to get V and U at state 1, A, B, and 2. So once again, use a different table here to get these properties. So, and then now you can start calculating the work, P dV. P is constant for all processes. You just need to update the V. So for example, process 1 is from state 1 to state A. So the work will be P times VA minus V1. So if you plug in all number, make sure that you include this conversion, then you get the number here. See there, it's very small, 0.003. And then you can calculate Q using equation 2 here. And then same thing, you can do it for the second process from A to B, and then from B to 2 here.